calculations. Yeah.
Why are we able to assume the collisions between the outer and inner molecules is a mass
Can you say it again, please? Thank you.
Why are we able to assume that the collisions are an accident and that like the kinetic energy is like conserved or
We're going to say, yeah, there will be elastic collisions, most of them, because really they probably never touch. There will be, we'll talk about electricity later on, because when they get really close together, the force becomes almost infinite. Yeah, yeah. So, yeah, we're going to assume they're elastic collisions. Even when they collide with gas molecules, they're here. We didn't talk about that subject yet. I think it would be probably next week. When they collide with a container, we're going to assume they're elastic, just for simplicity. Yeah,
Elastic or perfectly?
perfect. Yeah, no loss of energy. Yeah. Just like the ideal gas law is an idealization, right? It's a simplification. We don't want to deal with more complicated laws, and so we would simplify it like that. Yeah. Of course, anything can be made a little more complicated. But then they say, I always say it, when you're modeling something, you start with the simplest model that you can get away with, and then you can always add to it and make it more and more complicated, more and more realistic, until you get it as realistic as you can, or as you want. But if you want to start from the beginning with a model that includes everything, you will basically get nothing. You will not get anywhere. Right? You try to write an equation that includes every single possible thing, then you will not get anywhere. So it's always, you will always simplify. Just like in mechanics, if you remember, you started with objects have no shape. They're just point objects. You didn't care about their shapes, they were just points. And then we said, okay, now they have shape, so we can, when we apply a force here versus here, it can cause torques and so on. But at first, we ignored all that, right? We didn't worry about it. Then you add a torque, and then you considered systems of particles, more masses, and what happens to them, and so on. And then in here, we went back and we started to average, because you can't write Newton's second law for every gas molecule and say F equal to ma, and then try to predict its future. Why not? Why can't we say F equal to ma for each gas molecule? More complicated. Yeah. Yeah. You can predict the future, right? Using F equal to ma. Yeah, it is. It's actually pretty simple to answer. There are too many of them. You can't. Just 10 to the 23, 10 to the 25 of them. I mean, we barely could solve 3 equations, 3 unknowns by hand. Imagine 10 to the 23 equations with 10 to the 23 unknowns. It's too much. Okay. Let's just recap before we go on to calorimetry. What did we say thermal energy was? What was it to measure on? Yes?
Temperature?
Okay, so temperature was a reflection of, okay, temperature is a reflection of how hot or cold something is. Thermal energy is directly related to temperature, but it's not temperature itself.
changing heat.
Related to it, but not quite. Not quite heat, no.
Kinetic energy.
Yes. Thermal energy is literally the sum of all the kinetic energies of the molecules, of the individual particles. That is the thermal energy. So if I say, what's the thermal energy in this room, right? What's the thermal energy in this room? You would go, look at every particle that's moving, do 1/2 mv squared for it, right? Because that's the kinetic energy. Add them all up, that's your thermal energy. Okay? That's right. Thermal energy is a measure of all the total of the total kinetic energy of the system, right? Okay. Temperature is a reflection of how hot or cold. Quantizes of how hot or how cold something is, right? So thermal energy, temperature, they are related, but they're not the same. Now heat, what was heat? Just spoke about it. It's not thermal energy exactly. It's related, yeah. Between two things, because they have a difference in temperature. Yeah. So it goes from hotter to less hot, right? Yeah. And so it's energy transfer. And then work is macroscopic, right? Macroscopic, large. Let me see here. I think that's all I want to say. Thermal energy would be measured in joules. Heat is measured in joules. Work is measured in joules. Temperature is measured in Kelvin or Celsius or Fahrenheit. Some kind of a temperature scale. In all of these temperatures, the temperature will be absolute. Will be the Kelvin. Yeah, another thing is you cannot say, let's say I do work on the gas, I compress it, and I did work on it, right? And it will have some temperature. So the question is, what's the work in the gas? Can we say, is that a question? What's the work in the gas? That doesn't make sense. Work is a process. Same thing with heat. Heat is a process to transfer energy. So I can do work on this chair. I can push it, and the chair will have some kinetic energy after I push it. But I can say, while the chair is moving, what's the work in the chair? We can say how much work was done on the chair, how much work was done on the gas, but what is the work in the gas? I have no idea. It doesn't make sense. It's not a question you can ask. Same thing, how much heat is in the gas? That doesn't make sense. Heat is energy transferred because of the difference in temperature. Okay. The first law of thermodynamics, it says, it's a law, so you cannot prove it. You can only do experiments to confirm it. So it says the following. First law of thermodynamics, obviously, not of Newton, in this case thermo. It says, it asks the question, how do we change thermal energy? How do I change the thermal energy? Remember, you can only change the thermal energy if you change the temperature. So how do I increase the temperature of the system or decrease it?
Apply heat to it.
You can add heat to it or do work on it. Yeah, these two. So yeah, you can change the temperature or you can change the thermal energy by doing one of two things, or both at the same time. You can do work, let me write it this. You can do work on it, or add heat to it, or take away heat. The Q here is the heat. It could be positive, negative, or zero. It's zero if you don't add or take away anything. It's positive if you add heat to it. And it would be negative if you take away heat. Take away. And this is the work on it. Okay. That's the work on the gas. If you want to write it in terms of by the gas, you can write delta E thermal plus Q, but the W would be minus by the gas. Because on is the reverse, is minus sign of by. So that's the first one. That is the thermodynamics. As I remember, again, they said we're always imagining. We're not worried about the mechanical energy here. We're just worried about the thermal energy, the microscopic energy. When we say what is the kinetic energy of all the molecules are moving. I am not asking about if I take this container and throw it. Yeah, it has kinetic energy, but that's macroscopic. That's the one you study in physics one day. It's a fraction. The center of mass is not moving, but the molecules are moving. That's the one that this one reflects. That's the temperature. Okay. So, we know how to calculate work. Yeah, and then we're going to focus on heat for a little bit. Yeah.
So, just to make sure I get it, heat, work, and energy, they're not things that you can have, they're just things that are transferred. Or energy, they're all just energy that's been transferred.
Heat and work. Yeah. Thermal energy is something you can measure. You can say, what's the thermal energy of the system? That one, you're basically asking, what's the total kinetic energy of all the molecules of the system? This is called the first law, and that's the statement. So there are three special processes for the first law, thermodynamics. There's the isothermal process. If it's an isothermal process, what do I know about the temperature?
Constant.
Constant. So delta T is what? 0. If the temperature doesn't change, does the thermal energy change? No. The thermal energy is a reflection of the temperature. So if the temperature does not change, the thermal energy does not change. So for an isothermal process, this is true. Okay. Yes.
But the thermal energy is dependent with the work and heat.
Yes.
If there's no change in heat, is there any chance change in work?
They're independent of each other.
Oh.
Yeah. I can put that thing, the gas in a piston on the stove, and I can compress the piston. I can do both at the same time. So let's worry about them in a little bit. Okay. We will discuss it. Maybe it will become more clear as we discuss it. But yeah, they're independent of each other. You can have both. You can add heat and do negative work. You can add heat and do positive work. You can do any combination. So for an isothermal process, the thermal energy change is 0. So always ask it. It's isothermal. You're asked what's the change in thermal energy. You should answer 0. Next one is the isochoric process. Basically, I'm asking which of these is 0 for each of these processes. For isothermal, the change in thermal energy is 0. For isochoric, what is 0? The work. W is equal to 0. Again, if W is 0, there is no ambiguity saying W by or on. They're both 0. And then adiabatic, yeah, it is Q that is equal to 0. No heat is added or taken away from the system. Okay. And we're going to focus on calorimetry a little bit, where we're going to ask, let's say you have water at 10 degrees Celsius, how much heat is needed to raise the temperature to 70 degrees Celsius? Okay. Or you have ice, and then ice becomes water, and then the water becomes water at a higher temperature, how much heat was added? So that's calorimetry. Or I have a brick that's at 200 degrees Celsius, I throw it in a bath of water at 10 degrees Celsius, and the question is, what's the final temperature of the system? That's calorimetry. So that's what we're going to focus on at the moment. Okay. So with that, we will have to discuss what's called latent heats, and also the heat capacities of specific heats. Okay. So we have different phases. So let's talk about, for example, water. Here is time, and this is the temperature in degrees Celsius. Okay. Let's say I have water here at minus 100, or minus 50. Nothing special about minus 50. There's something special at 100. At 100, the water boils, right? Let's assume this is water that I'm talking about. So let's say it starts being ice at first, and you add to it, you add heat. As time goes on, you're adding heat. So as I add heat to it, let's say I have a block of ice, and I put it on the stove, and I slowly add heat. What happens to the ice?
Melts.
Okay, it melts. Does it melt immediately, or it has to go through minus 49, minus 48? So the temperature will rise slowly, so it will remain ice for a while. So, but the temperature will rise slowly until it gets to here. So you had ice at minus 50, and now you have ice at 0. You add heat, what happens? The ice starts to melt. So the ice doesn't melt immediately. So at some point, when all the ice, so we're saying we add heat slowly so that all the parts of the block of ice would have always the same temperature. It's not like the bottom part is touching the flame and then the top part is not touching it, and then they have two different temperatures. Assume I add the heat just one little bit at a time so that the whole block always has the same temperature. Okay? So when it gets to here, all of the block is at 0. It's ready to start melting. So you add 1 joule, a little bit will melt. You add another joule, a little bit more will melt. And you keep adding heat, and it will melt. It will keep melting. The heat that you add will just go into melting. So it goes from ice at 0 to water at 0. So it just melts. The temperature doesn't change, but the phase will change. So in this case, so it goes, I will draw it in, right? So for a while, you keep adding heat, but there will be phase change here. This is melting. Melt or freeze. Freeze if you're going the other way, if you're taking away heat, you're trying to freeze it. Melting if you go this way. Next, what happens? Now suppose it all melted. Now you have water at 0 degrees. All of it, all that block of ice has become ice at 0, and now it becomes water at 0. So you have it all water at 0. What happens next? You keep adding heat. Water will at a higher and higher temperature. Good. So it will become water at higher, higher, and higher, and higher temperatures until it reaches 100, right? 100. So it starts to do what? Oil, and you have vapor, right? So it remains, you keep adding until all the water boils and becomes vapor. Then what? You keep adding heat to that vapor.
Heats up.
You have, and steam at a higher temperature than 100. Maybe steam at 105, at 110, 150, at 200. Keep adding heat. So this is steam. In this case, that's at higher temperature. So this one here is boiling or condensing. So notice, during the melting or freezing, boiling, condensing, the temperature doesn't change. But there is a process going on. It's changing phase. It's going from one phase to another. Going from solid to liquid, or maybe from liquid to gas. Okay. So there are two equations that govern it. So when the temperature is changing, and T is changing, suppose you add heat. Here's heat. You add heat. What does the heat do if the temperature is, let's say you have water at 10 degrees, and I add heat, what happens? The temperature should change, right? The more heat I add, the more change in temperature I get. Okay? And is it the same way? Let's say I have 1 gallon of water versus 10 gallons. Will the heat affect them the same way? The more you have, the less effect, right? You have to add more heat. So it's actually proportional to the mass that you have. Okay. And does water change its temperature Does it react to heat the same way iron does? No. Which one is easier to heat? Iron, right? Iron is easier to increase its temperature than water. And so there would be something here that is proportional, that has to do with the material itself, and that's called the specific heat. So let me just, this Q is heat, M is mass, C is specific heat. I will give you some values of specific heat. Give some values for different specific heats. And this is change in temperature. Change in temperature. So here are some specific heats that I would put. So for aluminum, sorry, not copper, iron, steel, and I put water, ice, and ethanol. Like alcohol. And here is the specific heat in joules per kilogram per Kelvin, or degrees Celsius, either way. And someone remind me why it's okay to say per joule per kilogram per degree Celsius, and I say that's the same as saying per Kelvin. Yeah.
It's because the variable, the temperature in the equation is change in temperature. Therefore, because the change in Celsius and Kelvin are the same, they'll be the same.
Good. Yeah. A change of 1 Kelvin is the same as a change of 1 degree Celsius. I'm not saying 1 degree Celsius is equal to 1 Kelvin. I'm saying a change, an increase of 1 degree Celsius would be an increase of 1 Kelvin. Okay? Because you go from degree Celsius to Kelvin, you just add 273. The difference between them is the change. So in this case, for the delta T, it can be in Kelvin or degree Celsius. As long as you're consistent, the change is going to be the same. So let me write down those values. So for copper, this number here is 385. For iron, it's 449. For water, it's 4,186, 41.9 approximately. For ice, it's going to be 2090, and ethanol is 2400. The lower the specific heat, the easier to change the temperature. The higher the specific heat, the harder it is to change the temperature. I mean, if you put a spoon on the stove, the temperature gets hot quickly, right? But if you put a pot of water on the stove, the water temperature is not going to change quickly. It takes a while to boil water. So the higher this number, the harder it is to change the temperature. Given the same number of kilograms. All right. So that's that. Now, how about this melting and boiling and so on? Well, for melting and freezing, we have what's called latent heat of vaporization, latent heat of fusion. So we have what's called latent heat of fusion, and we will do an example in a second. So we have, it says Q. You add if it's about to melt or about to freeze, you're adding heat or taking away heat, but the temperature is not changing. So what's happening? It's changing phase, and that heat will change the phase, and it's M times L F, and it's plus or minus. I will tell you what plus or minus means in a second. This LF is latent heat And for boiling or condensing, Q is also plus or minus the mass times L V. And it's latent heat of vaporization. Of vaporization. Still have about 20 minutes or so, right? So I want to go over 3 examples on this to basically explain how these equations work, and then hopefully we get to the next topic. So let's. First example is we have a student who is yeah.
If you're freezing or condensing, then you would use liquid.
Yes, yes, because you have to take away these. We'll do an example in a second. By the way, how many people in, we'll get to your question, in chemistry who have this stuff?
We didn't really, like, the Q equals plus minus and latent heat of fusion. Our equation didn't look exactly like that, but we
Okay.
had something very similar, like the MC delta T we use that.
MC delta. They're usually the gas. Usually, if it's a solid or a liquid, the work done would just be zero. They're incompressible. We would just worry about the work done if it's a gas. That's when it's compressible. Yeah.
I just noticed, is the fact that that you need to apply heat in order to get past the latent diffusion or vaporization, is that the reason why it's considered its own thing from thermal energy? Because when you apply heat, instead of becoming thermal energy during phase change, it's just used up. If that makes sense.
When it changes phase, the molecules for the ice, they're moving slower than the water. They're equivalent of zero.
Uh-huh.
Yeah.
So I guess my question would be, oh yeah, that covers it.
Okay, perfect.
Okay.
So let's look at, I think it would be more clear probably
No,
as we go. So you have a student, it says here, catches the flu, the student is 70 kilograms. So let's just do that. So here is a student, 70 kilograms, right? And what's normal temperature? It's about 37 degrees, yeah. For regular, if you're healthy and all that stuff, it's about 37. In Fahrenheit, 98.6. Yeah. Let's say the student says catches the flu. This same student now has a temperature of 39 degrees Celsius, which is about 102.2 Fahrenheit. It's the same student, so it's the same mass, okay? And the question is, how much heat is required to raise this student's body temperature from 37 to 39? By the way, in Kelvin, this would be plus 273, that's 310. And this one would be 312, right? So what's the change in temperature? 2. And what's the change here? 2. So you see the change, whether it's Kelvin or degrees Celsius, is going to be the same. So Q would be, it's a change in temperature, so MC delta T. What's the mass in this case?
70.
Oh. I'll worry about C in a second. Delta T is 2 Kelvin or degrees Celsius. Now C, the student. Student is a person. And so they're made mostly of water. And water has this specific heat. So if we knew nothing else, we'll just use this as the specific heat. The book tells us, or the example tells us, that the for mammalian body, the specific heat is about 34. Somebody did this experiment, and they came up with this number. It's 34. Okay? So it's slightly less, a little bit less than that. 34. And so we get the heat, and it is 4.8 times 10 to the 5th joules. And since it has to do with the person's heat, so I would like to talk about calories. Turns out to be about 114 calories with a capital C, kilocalories. Next example, I'm going to, let's involve this latent heat of fusion. Okay. Or latent heats somehow. So here is the next example. I have how much, the question is how much heat is needed to transform 2 kilograms of ice at minus 10 degrees Celsius into water at 30 degrees Celsius. So how much heat is needed? So you have to go through these kinds of problems a little bit carefully. I'd like to draw a box like this. Here's ice. It's at minus 10. It first becomes what? It becomes ice at what? 0 degrees Celsius. And then what?
Phase change.
Phase change. So it becomes water at also 0 degrees Celsius. And then it becomes water at 30 degrees Celsius. Okay? So I'm going to, so this one here, this is the heat required, Q1, to accomplish this, to go from ice at minus 10 to ice at 0. And then Q2 is the heat required to melt ice at 0 into water at 0. And then Q3 is the heat needed to increase the temperature of water from 0 to 30. So the total heat needed is Q1 plus Q2 plus Q, all 3 okay. Let's add them. For Q1, what should I write?
MC over.
Good. It's a change in temperature. The temperature is changing, so M C with C.
C ice.
Ice, good. Because we still have ice. Yeah. Times delta T. What should I put for the temperature?
ML at 10. 10.
It would be, it's gonna be The final temperature is 0, the initial is minus 10. So I'm just going to be, yes, it is 10, but I'm going to do it a little more carefully, like this. Okay? But once you know, and you're familiar with it, feel free to skip ahead. Because 0 minus 10 is 10. The next one is going to be the phase change. Okay? Next one is going to be the phase change, and it's latent heat of fusion. And it's going to be this. Notice this one says plus or minus. Are we going to add heat or are we going to take away heat? Add. So we'll go with the plus. So we're adding heat. So that's what the plus or minus. So plus. Yeah. The mass times the latent heat of fusion, right? I put LF. And where do we get this number? From tables. And I will give you the number in a second. And then plus the mass. By the way, the mass is the mass. It's 2 kilograms. You can't change that. You're not taking away the water or chunks of the ice. It's going to be the whole 2 kilograms. Now the mass times the specific heat of what? This step. Yeah. So now that ice is no longer ice. It's water. From 0 to 30, all the way to 30, it is water. So CW, W for what? Times delta T will be 30 degrees. The final minus the initial, what is it? Q. The mass is 2 kilograms. For ice, it's 2090, right? I wrote it over there. 0 minus 10 is 10. Plus. Now, in here, it's 2 kilograms times this latent heat of fusion. Well, if you go in the book, or my notes, you got a big table. And you look it up. It says, it gives you the melting point, the boiling point, and I scroll down to water. It melts at 0. Ice melts at 0, or water freezes at 0. And LF is 3.34 times 10 to the 5th. 3.34 times 10 to the 5th. The units would be joules per Kelvin, right? Because at the end, the answer is going to be joules. Plus, and the mass here is 2. Specific heat of water is 4190. And then I don't have the number for this, so I would rely on it. Like this? Okay. I'll take that. Everybody should try to do it. So it would be something. I think 10 to the 5th sounds reasonable. Exactly how much it is. Okay, perfect. And then the last one is, we're going to do more in the worksheets on this in the homework.